Some worlds feel real the moment we see them, not because they resemble anything we have touched, but because they borrow just enough from real science to slip past our skepticism. A moon like Pandora seems impossible at first glance, then strangely plausible the longer you stare at it. A desert like Arrakis feels exaggerated until you remember how many cruel worlds the universe is fully capable of producing. Science fiction often works this way. It invites us into places that look like dreams, then quietly anchors them to physics, biology, and astronomy. But that raises a deeper question. When cinema shows us the cosmos at its most beautiful or terrifying, where does the science end and the fiction truly begin? There is a particular kind of illusion that only space movies can create. On Earth, we instinctively know what is reasonable. We know what skies should look like, how water should move, how far a horizon ought to stretch. But once a story leaves our planet, most of those instincts become unreliable. Suddenly a glowing moon, a storm-racked gas giant, a world with kilometre-high waves, or a creature with acid for blood can seem equally believable. Space is already so strange that fiction has room to hide inside reality, without us always noticing where the line was crossed. That is part of what makes science fiction such a powerful form of storytelling. At its best, it does not simply invent wonders, it builds them on top of ideas that are already extraordinary. The universe really does contain planets around other stars, moons beneath frozen crusts, radiation storms, black holes, time dilation, and life on Earth so bizarre it already resembles alien design. So when a filmmaker bends those truths, even slightly, the result can feel less like fantasy and more like a hidden branch of nature we have not yet discovered. And that is why certain fictional worlds stay with us. Not just because they are visually unforgettable, but because they seem to ask something of us. Could this exist? Would this actually happen? If we travelled far enough, learned enough, and survived long enough, might we one day stand beneath a sky like that and realise the movie was not entirely wrong? One of the clearest examples is Pandora from Avatar. It is introduced as an Earth-like moon in the Alpha Centauri system, lush with forests, oceans, flying creatures, and a biosphere so richly interconnected that it seems to behave almost like a planetary nervous system. Human civilization, having exhausted much of Earth's natural wealth, looks outward and finds in Pandora a world worth crossing interstellar space to reach. Even before we begin examining the science, that premise touches something real. If humanity ever expands beyond Earth, it will not do so because the journey is easy. It will do so because the destination feels irresistible. Pandora's great cinematic trick is that it looks immediately familiar while being built from a different cosmic arrangement than Earth. It is not a planet orbiting a star. It is a moon orbiting a giant planet called Polyphemus, which in turn orbits a star in the Alpha Centauri system. That already places it in a very different category from the worlds we usually imagine when we talk about habitability. We tend to picture an Earth-like planet circling at just the right distance from a sun-like star, warmed enough for liquid water and sheltered enough for long-term stability. Pandora suggests another path. Perhaps the right conditions for life do not have to exist only on planets. Perhaps moons can inherit those conditions too. That idea is not nearly as far-fetched as it may sound. In our own solar system, moons are everywhere. In fact, there are far more moons than planets, which means that if nature has many ways to assemble habitable environments, moons may be among its most common experiments. We already know of icy moons such as Europa, Ganymede, and Enceladus that may hide oceans beneath their frozen surfaces. None of them look anything like Pandora, but they show us something important. A moon does not have to be dead. It can hold water, internal energy, chemical gradients, and perhaps even life. So the moment Avatar chooses to place its living world on a moon rather than a planet, it is not abandoning science. It is leaning into a possibility the universe may actually favour. The more difficult question is whether a moon could resemble Pandora specifically, with surface oceans, dense forests, breathable air for native life, and enough stability to support a vast and complex ecosystem. To even begin answering that, we have to start with location. The films place Pandora in the Alpha Centauri system, our nearest stellar neighbour, roughly 4.37 light-years away. In human terms, that is unimaginably distant. A spacecraft moving at the speed of Voyager 1 would need more than 70,000 years to get there. So any human presence around Pandora already assumes a civilization far beyond our current propulsion abilities. In other words, the movie is asking us to accept one major technological leap before we even arrive. But once we do arrive, the choice of Alpha Centauri is actually clever. It is not a random star system thrown into the script because it sounds scientific. Alpha Centauri A is a sun-like star, a little larger and brighter than our own sun. That matters because stars of that kind can host habitable zones, regions where temperatures allow liquid water to exist on a rocky surface under the right conditions. Pandora itself is not orbiting the star directly, but its parent planet could occupy such a zone, allowing a moon around that planet to receive an amount of starlight broadly compatible with Earth-like conditions. That is where the first layer of plausibility settles in. A gas giant in a habitable zone may sound unusual, but it is not forbidden. If such a world exists, then large moons around it become natural candidates for habitability, and large moons may have advantages. They can be tidally heated by the gravity of the giant planet. They can inherit a complex orbital environment. They may even benefit from magnetic effects or atmospheric retention, depending on their mass and composition. The same arrangement that creates danger can also create dynamism. Of course, the danger is real. A moon orbiting a gas giant would not simply enjoy a grand view. It would live inside a hostile gravitational and electromagnetic neighbourhood. Giant planets tend to have powerful magnetic fields, and those fields can trap huge numbers of energetic particles. Around Jupiter, for example, the radiation environment is severe enough that any unprotected surface life would face extraordinary stress. So if Pandora sits deep within a similar radiation belt, its biosphere should be under constant assault. This is the first place where Avatar earns more respect than it is often given. The film does not dwell on particle flux, magnetospheres, and ion bombardment, but it hints that Pandora is not an ordinary environment. The auroras are one clue, the floating Hallelujah Mountains are another. Both suggest intense electromagnetic phenomena. Even if the exact mechanisms shown on screen are highly stylized, the world feels shaped by powerful forces. It does not feel like Earth wearing blue makeup. It feels like a moon that has evolved under stresses Earth never had to endure. And that matters because believable science fiction is rarely about getting every equation perfect. It is about creating a world where consequences seem connected. If you place life on a moon of a gas giant, then that life should bear the imprint of radiation, tides, unusual skies, and a more complicated relationship to day and night. Pandora, in broad strokes, does. The day-night cycle is one of the most elegant examples. On Earth, sunrise and sunset are simple facts of rotation. On a moon like Pandora, things become more layered. If the moon is tidally locked to its giant planet, one side always faces that planet, just as our moon always presents the same face to Earth. That would mean Polyphemus could loom in one region of Pandora's sky without wandering across it. For inhabitants on the near side, the giant planet would be a permanent celestial presence. On the far side, it would never be seen at all. Already the psychology of such a world begins to diverge from ours. Imagine building a civilization beneath a sky where a giant striped planet never rises or sets, but simply hangs there forever, changing only in light and shadow. Imagine another civilization on the opposite hemisphere, with no direct visual evidence of the planet they orbit. Two societies on the same moon could inherit completely different cosmologies from the same mechanics. Then come the eclipses. If Pandora passes through the shadow of its parent planet, the star would be briefly occluded, producing a regular dimming event more dramatic than anything most humans ever experience on Earth. Not a rare spectacle that happens once in a generation, but a recurring part of life, and because the system has more than one star, the darkness would not necessarily be complete. Instead of a simple plunge into night, the world might shift into an uncanny twilight, with the secondary star still illuminating the landscape and bioluminescent life intensifying the effect. That is exactly the kind of detail that helps a fictional world feel inhabited rather than decorated. Pandora's night is not just dark for the sake of visual beauty, it is dark in a way that follows from where the moon is and what surrounds it. The science may not be specified in the dialogue, but the atmosphere grows out of orbital logic. A beautiful choice becomes a physical one. The atmosphere itself pushes that balance between imagination and plausibility even further. In the films, Pandora's air is rich in gases that humans cannot safely breathe, including high levels of carbon dioxide and other toxic components. For human visitors, that means masks and filtration. For native life, it means evolution under conditions very different from our own. This is an important correction to a common habit in older science fiction, where alien worlds somehow end up with human-friendly air simply because the plot needs people to walk around without helmet. Avatar resists that convenience. Pandora is visually welcoming but chemically alien. That single choice adds credibility because it reminds us that habitability is always relative. A world can teem with life and still be lethal to us. Human beings often treat Earth conditions as if they were universal. In reality, they are local. They are the result of one planet's specific history. On another world, life would adapt to another baseline. This helps explain why Pandora's organisms are not just reskinned terrestrial animals. The Na'vi are taller, leaner, and physically tuned to their environment. The reduced gravity makes larger bodies easier to support. A denser atmosphere changes the behavior of movement and sound. If oxygen levels are higher, that affects metabolism and the scale of biological growth. On Earth, prehistoric oxygen-rich periods may have helped support larger bodies and more energetically intense ecosystems. Pandora extends that idea into an alien biosphere, creating forests and creatures that feel exaggerated but not untethered. Even so, every layer of plausibility comes with another question. Reduced gravity helps, but how much? Dense air aids lift, but how far can that go? Radiation can be shielded, but by what exact combination of magnetic field, atmosphere, and orbital placement? This is where science fiction starts to reveal its deeper craft. The goal is not always to answer every question perfectly. It is to answer enough of them that the remaining mysteries feel stimulating rather than distracting. Pandora succeeds because it gives the impression of a world built under pressure from real forces. Its oceans are not just there to be beautiful. Its eclipses are not just there to be poetic. Its atmosphere is not just there to inconvenience the humans. These features all appear to emerge from a single physical setting. The moon, the gas giant, the nearby stars, the chemistry, the gravity, and the biosphere all seem to belong to one another. And that is what separates the most memorable space worlds from mere fantasy landscapes. They do not simply ask whether something looks wondrous. They ask whether the wonder has a cause. They make beauty answer to structure. They make terror answer to environment. They make the impossible feel one scientific step away from possible. The longer you sit with Pandora, the more it begins to function not as an escape from physics, but as an invitation back into it. The world seems magical at first, because we encounter it the way explorers always encounter the unknown, by noticing effects before causes. We see luminous forests before we think about atmospheric chemistry. We see floating mountains before we think about magnetic anomalies. We see graceful bodies leaping through alien jungles before we think about gravity, density, and energy use. But the questions accumulate, and once they do, the beauty of the world starts to change. It becomes less decorative and more diagnostic. Because if Pandora can be even partly defended by science, then the real universe may be hiding stranger places still. Worlds that do not need our imagination to be extraordinary, only our patience to understand what sort of sky they were built beneath. That sort of sky begins with motion. A moon like Pandora cannot simply sit in a convenient pocket of warmth and leave the rest to chance. It has to survive a complicated dance between its star, its giant planet, and its own internal structure. The more closely you examine that dance, the more remarkable Pandora becomes, because nearly every breathtaking feature of the world depends on orbital compromise. The first compromise is tidal locking. If Pandora always keeps the same face turned toward Polyphemus, then the giant planet becomes a permanent fixture in the heavens for anyone living on the near side. It would not drift slowly across the sky the way our moon does from Earth. It would hover in roughly the same place, enormous and inescapable, growing brighter or dimmer as the angle of sunlight changed. For any intelligent species evolving beneath that view, the planet above would not feel like an object in the sky. It would feel like part of the sky itself. This has consequences that go far beyond scenery. Tidal locking means that Pandora's rotation period and orbital period around Polyphemus are the same, so the familiar rhythm of day and night is no longer just a matter of spinning beneath a star. It is filtered through a more complex geometry in which the giant planet can cast a shadow, reflect light, and alter the visual texture of time. Some regions would know regular eclipses as part of ordinary life. Others might experience long stretches where Polyphemus glowed overhead like a second world, bright enough to shape the habits of nocturnal organisms and perhaps even the timing of migration, hunting, and reproduction. On Earth, night has one basic meaning. The sun drops below the horizon and the world cools into darkness. On Pandora, darkness would be more conditional. The stars in the Alpha Centauri system do not provide the same kind of steady illumination as a second sun in a fantasy sky, but their presence could still complicate the quality of twilight. Add to that a luminous biosphere, and night becomes less like an absence of light and more like a transition into another ecological mode. That helps explain one of Avatar's most striking impressions. Pandora does not merely go dark after sunset, it seems to wake differently. There is something scientifically satisfying about that. On Earth, bioluminescence already exists across many branches of life. We find it in fungi, insects, jellyfish, plankton, and deep-sea organisms. It evolved for different reasons in different lineages, from communication to camouflage to predation. So when Pandora fills its forests with glowing plants and living signals, the idea is not absurd on its face. It is an extrapolation from known biology. The real question is whether an entire ecosystem could lean so heavily into visible luminescence without wasting enormous amounts of energy. That depends on the environment. In a world shaped by frequent dusk-like conditions, by thick atmosphere, by unusual spectral filtering from a gas giant-dominated sky, and by ecological relationships built over immense spans of time, light could become a far more valuable biological tool than it is for most life on Earth. If organisms can communicate, attract pollinators, deter predators, or synchronize behavior through low-energy light production, then natural selection may reward luminescence more strongly than it does here. The glow of Pandora may look magical, but its logic is evolutionary. It suggests a world where visibility itself became a survival strategy. Then there is the matter of gravity. Pandora's inhabitants move with a fluid athleticism that feels slightly more effortless than human movement. Creatures leap farther, bodies seem tall and elongated, flight appears almost too graceful. This could easily have been treated as pure cinematic style, but the world building offers a partial physical explanation. Pandora's gravity is lower than Earth's, which would reduce the energy cost of jumping and help support larger, more lightly built organisms. That part is reasonable. If the Moon is somewhat smaller or less dense than Earth, reduced surface gravity follows naturally, and reduced gravity changes biology in subtle but profound ways. Limbs can be longer, vertical movement becomes cheaper, falls become less punishing. Tree canopies may support different ecological structures because mass behaves differently in motion. Even the architecture of muscle and bone would evolve under another baseline. The Na'vi look the way they do not only because the film wants them to appear alien, but because a world with lower gravity would likely produce bodies that do not carry themselves the way ours do. But gravity alone is never enough. If you want flying mountains, giant aerial predators, and floating seed-like organisms drifting through the air, then you also need an atmosphere that helps carry those bodies. Avatar leans into this by making Pandora's atmosphere denser than Earth's. That does two things at once. It helps justify the ease of flight, and it changes how the world should feel at every scale. Sound would behave differently. Smells might travel differently. Falling objects would resist descent more strongly. Wings could generate lift more efficiently. The boundary between gliding and powered flight would shift. This is why Pandora's life feels coherent, even when it is stylized. The ecology is not built on one miracle. It is built on multiple, moderate departures from Earth conditions that reinforce one another. Lower gravity alone might not give you the beauty of the aerial world we see. Denser air alone might not either. But combine them, and suddenly larger flyers, slower falls, and sweeping motion through vertical landscapes become much easier to imagine. The most famous example is the Ikran, often called the Banshee, whose flight would look implausible under Earth conditions if its mass were too high relative to wing area. Yet on Pandora, lower gravity reduces the weight burden, while denser air improves lift. The result still demands some generosity from the viewer, but not infinite generosity, and that is often how the best speculative design works. It does not aim for absolute proof. It aims to move the idea out of the impossible and into the arguable. The same is true for the enormous trees and jungle architecture. On Earth, height is limited not only by access to sunlight, but by structural stress, water transport, and the metabolic cost of maintaining massive living forms. Lower gravity can relax some of those structural constraints. If the atmosphere and nutrient cycles also differ, then biological scale may expand accordingly. Pandora's forests, then, are not just oversized because bigger looks impressive on screen. They may be oversized because the moon's physics make vertical life more affordable. And yet, one of the most iconic features of Pandora seems to go beyond affordable and into outright impossible. The floating mountains are visually unforgettable because they violate one of our strongest expectations about matter. Mountains are supposed to rest on something. They can erode, collapse, fracture, and rise through tectonics, but they do not simply hover. So if Pandora wants us to accept airborne rock formations, it must offer a force powerful enough to oppose gravity at enormous scale. The film hints at that answer through unobtainium and magnetic anomalies. The implication is that certain materials in the crust interact with Pandora's magnetic environment in such a way that large landmasses can remain suspended. This is where the world's science becomes much more speculative, but not entirely random. Magnetism is real. Levitation through magnetic forces is real. Diamagnetic materials can be repelled by strong magnetic fields, and superconducting systems can create stable levitation under the right conditions. What strains credibility is not the existence of magnetic levitation itself, but the scale involved. To hold mountains aloft, the fields and material properties would need to be extraordinary, far beyond anything we see in natural terrestrial geology. The energy relationships would be immense, stability would become a problem, weathering, collisions and structural fracture would all threaten the equilibrium. In other words, this is the point where Pandora makes its boldest bargain with the audience. It says everything else about this moon may be grounded enough to earn trust, so perhaps you will grant us one beautiful impossibility. And strangely, the bargain works. It works partly because the floating mountains are not isolated nonsense. They are embedded in a wider environment already shaped by electromagnetic drama. The auroras, the strange mineral interest from humans, the visual language of charge and luminosity, all prepare the viewer to accept that Pandora has geophysical behavior unlike Earth's. The mountains become not a single unearned trick, but the climax of a larger pattern. Auroras themselves tell us something important about the moon's environment. On Earth, auroras occur when charged particles from the solar wind interact with our magnetic field and atmosphere, funneling energy toward the poles and exciting atmospheric gases into glowing displays. Around a giant planet, those interactions can become much more intense. Jupiter's magnetosphere, for example, is enormous and complex, shaped not only by the Sun, but by the motion of its moons and plasma environments. A moon inside such a system could experience electrical interactions far more dramatic than anything we see here. So when Pandora's skies shimmer with colour, the effect is not just decorative world building. It suggests a moon immersed in a live electromagnetic system, constantly exchanging energy with its parent planet and surrounding space. That would have biological implications too. If the surface receives more radiation than Earth, then life must adapt. Perhaps the dense atmosphere helps provide shielding. Perhaps Pandora has a magnetic field of its own, or benefits from position within a larger protective geometry. Perhaps organisms evolved repair mechanisms, pigments, or behaviours that reduce exposure during hazardous periods. Again, Avatar rarely spells this out, and perhaps it should not. A film can lose its spell if it stops to lecture every time the scenery changes. But the signs of adaptation are there. Pandora feels like a world that does not welcome life casually. It hosts life magnificently, but only because life has learned to answer the conditions imposed on it. That is one reason the Na'vi themselves feel more convincing the longer you think about them. Their height and strength make sense in lower gravity. Their ability to move with speed through forest canopies reflects a world where three-dimensional mobility matters. Even the neural cue used to bond with animals and biological interfaces, while deeply speculative, reflects a larger theme of ecological integration. Pandora is not presented as a planet of isolated organisms. It is presented as a networked world where life forms interact with extraordinary intimacy. There is no direct Earth analogue for that exact mechanism, but there are hints in real biology that make the idea less alien than it first appears. Trees on Earth exchange resources through fungal networks in soil. Bacteria communicate chemically. Nervous systems encode signals electrically. Symbiosis shapes everything from coral reefs to human digestion. What Avatar does is condense those diffuse biological truths into a more visible and emotionally legible system. It takes interdependence, something real and often hidden, and gives it a dramatic interface. This may be the film's most sophisticated scientific instinct. Pandora is not just habitable in the narrow sense of temperature and water, it is biologically entangled. The world behaves as if evolution has had enough time and enough selective pressure to produce not merely diversity, but connection at ecosystem scale. That is speculative, certainly, but it grows from an authentic observation about life. Organisms do not survive alone for long. They survive through relationships. The human presence on Pandora sharpens that contrast. For people arriving from Earth, the moon is both valuable and dangerous. It contains resources worth extracting, but it resists easy occupation. Its air cannot be breathed. Its creatures are stronger than expected. Its terrain is complex, vertical, and difficult to mechanize. In a sense, Pandora does what a believable alien world should do. It refuses to flatten itself for human convenience. That refusal is one of the strongest markers of scientific maturity in fiction. Truly alien environments should not automatically align with our needs. They should challenge our assumptions about what counts as normal, safe, and beautiful. Pandora does this with unusual elegance. It seduces the eye while constantly reminding the body that it does not belong to us. And the more persuasive the world becomes, the more an unsettling thought begins to form. If a moon like Pandora can seem even partly plausible, then the universe may be richer in living possibilities than we usually admit. Not necessarily rich in worlds that welcome humans, but rich in worlds that welcome life under rules different from ours. Once that door opens, the imagination changes. Alien life no longer has to emerge only on a second Earth. It can emerge on moons, under strange skies, inside difficult chemistries, in places where habitability is not comfortable but conditional. That is where the deeper purpose of worlds like Pandora starts to reveal itself. They are not merely fantasies of escape. They are rehearsals for humility. They remind us that life is not an ornament placed on a convenient planet. It is an adaptive force, capable of exploiting niches we would once have dismissed. And if cinema can lead us into that realization through forests that glow and mountains that hover, then it has done more than entertain us. It has shifted our sense of what nature may be allowed to do. But Pandora is still generous compared with what science fiction sometimes demands from its worlds. It offers water, forests, breathable air for its native species, and the suggestion of ecological harmony. Other fictional worlds ask a harsher question, not how life flourishes in abundance, but how civilization survives in near-permanent scarcity. And nowhere is that question more iconic than on Arrakis. Arrakis feels convincing for almost the opposite reason that Pandora does. Pandora persuades by abundance. It overwhelms you with lushness, motion, and biological possibility, until you begin to believe that life could exploit almost any favourable corner of the cosmos. Arrakis works through deprivation. It takes away rivers, forests, clouds, comfort and ease, then asks whether a world stripped down to heat, dust and scarcity could become even more important than a paradise. That is why it lingers in the imagination. It does not promise that the universe will be kind. It suggests that the most valuable world in a civilization may be one that seems almost impossible to live on at all. Dune is often remembered for its politics, religion and mythology, but beneath all of that is a planetary question. What kind of world would produce a culture like this? What kind of astronomy would make water the most sacred substance in daily life, while a single desert resource shapes the economy of an interstellar civilization? Frank Herbert understood something essential about believable world building. A planet does not just provide a backdrop, it pressures everything built upon it. It shapes architecture, language, ritual, diet, war, memory, and power. The Dune universe spans many worlds, but 3 of them define its emotional and physical contrast. Giadi Prime is the industrial centre tied to exploitation and excess. Caladan represents abundance, water, and the memory of gentler climates. Arrakis stands between them not as a balance, but as an extremity. It is the place where empire reaches for wealth and discovers that wealth is embedded in a world so severe it resists control at every level. That is what gives Arrakis its force. It is not just dry, it is dry in a way that reorganizes civilization around survival. The astronomical setup begins with its star. Arrakis is described as the 3rd planet from Canopus, orbiting at a mean distance of roughly 87 million kilometers. Taken at face value, that sounds dangerous. Earth orbits the Sun at roughly 150 million kilometers, and even that relatively modest distance is what keeps our surface temperatures compatible with long-term liquid water. Move much closer to a bright star, and the energy balance shifts quickly. More radiation, more heating, and a greater struggle for any atmosphere or hydrological cycle to remain stable in familiar form. So could Arrakis really support human life at that distance? Under an ordinary Sun-like star, the answer would seem difficult, but Canopus is not ordinary. In the logic explored around Dune, the star may, at some stages, have been cooler and dimmer than we might assume from its current stellar identity, placing Arrakis, at least temporarily, in conditions more favourable to life. This is one of those cases where the fiction does not become fully secure, but it does become more interesting. Rather than imagining a static planetary environment, Dune hints at a world whose habitability may depend on a changing stellar context. Arrakis starts to feel less like a timeless desert and more like a planet carrying the memory of a different cosmic past. That possibility matters because deserts do not exist in a vacuum. Even the harshest deserts on Earth are embedded in a larger planetary system that still contains oceans, atmospheric circulation, and global water storage. Arrakis appears to have gone much farther. It presents the viewer with a world where dryness has become civilizational destiny. For that to happen, climate alone is not enough. You need geology, atmosphere, orbital behavior, and ecological history all leaning in the same direction. The planet must not merely experience aridity, it must be trapped by it. This is where Dune becomes especially intriguing, because Arrakis is not described as a simple, isolated world moving quietly through space. On either side of it are two much larger neighbouring planets, often referred to as the twins. Their elliptical orbits create a gravitational tug that reportedly disturbs Arrakis and contributes to an unusually unstable orbital pattern. A year on Arrakis can vary dramatically, from roughly 295 to 595 standard days. That is an extraordinary claim. If true in a literal physical sense, it would mean Arrakis lives in a profoundly dynamic celestial environment, one in which the regularity we take for granted on Earth has been replaced by an almost living instability. There is a seed of realism inside that idea. Highly elliptical orbits do exist. Gravitational interactions between planets can create long-term perturbations, orbital resonances, and changes in eccentricity or inclination. Our own solar system contains echoes of this kind of complexity, though usually on much gentler terms than Dune suggests. The problem is scale. To create year-length changes that large in a way consistent with long-term planetary survival would demand a very unusual and potentially chaotic configuration. At some point, the same interactions that make the system interesting would begin to threaten its stability. And yet the idea is dramatically perfect for Arrakis. A world already defined by uncertainty at the ecological level is made uncertain at the orbital level too. Even the calendar becomes unstable. Time itself resists domestication. That is why Dune's astronomy feels persuasive in an emotional sense, even when it becomes shaky in a strict astrophysical one. The motions of the heavens reinforce the world's deeper identity. Arrakis is a planet where nothing essential can be taken for granted. The moons continue that pattern. Dune's visual language makes them central to the atmosphere of the world. They are not incidental points of light. They are part of Arrakis's psychological architecture. On Earth, our moon stabilizes the tilt of our rotational axis over long periods, helping preserve relatively moderate climatic behavior. Remove a large moon from Earth's history, and our seasons and long-term stability might have looked very different. So the idea that moons could influence planetary behavior is not fantasy. It is one of the reasons our own world is as stable as it is. But Dune pushes that principle farther. It suggests a system where orbital neighbours and moons participate in shaping a world that feels perpetually on edge. That is dramatically potent, though physically the details become strained. The exact combination of variable years, nearby large planetary companions, and still manageable surface conditions asks for a system balanced almost too precisely between habitability and chaos. Real planetary systems can be surprising, but they are usually unforgiving about arrangements that flirt too closely with instability for too long. Still, Arrakis does not need to pass every orbital stress test to succeed as science fiction. Its brilliance lies in how it translates celestial conditions into lived experience. On a planet where heat defines every decision, daily life would become a discipline of conservation. Motion itself would be strategic. Shelter would matter more than status. Clothing would not be fashion first, but physiology by proxy. The body would become a technology for holding on to water, and culture would form around the reality that survival is never assumed. This is one of the strongest scientific instincts in Dune. Herbert understood adaptation. Not adaptation in the narrow genetic sense alone, though that matters, but adaptation as a total social process. If a population survives on a world like Arrakis for generations, their worldview would inevitably be shaped by scarcity. They would not think like people from a temperate river valley. They would not build like people from a rainy coastline. Their myths, rituals, and moral instincts would be drawn from the environment's demands. Water would no longer be a background substance. It would become memory, power, and sacred measure. Earth offers many smaller versions of this lesson. Human societies in deserts have always developed intimate relationships with storage, shade, seasonality, and movement. Where water is rare, knowledge becomes a survival tool. Roots matter, wells matter, discipline matters. Arrakis scales that truth to planetary level. The Fremen do not merely inhabit a desert, they are a civilization defined by mastering the logic of that desert more deeply than any outside force can. That may be why Arrakis feels so much more convincing than a purely symbolic desert world would. It is not hot just to look dramatic. The heat governs behavior. It explains why bodies are covered, why water is collected obsessively, why cities and settlements feel like fortresses against the environment, and why outsiders so often misunderstand the planet's true rules. A believable world always creates knowledge gaps between those shaped by it and those merely passing through. Arrakis is full of those gaps. Of course, the most iconic feature of the planet is not simply the absence of water, but the presence of sandworms. In purely biological terms, creatures of that immense size raise immediate questions about metabolism, locomotion, heat regulation, and the physical properties of the sand itself. The larger an organism becomes, the harder it is to move, feed, and maintain structural integrity. Earth's own history sets limits on what large animals can do, especially on land. A giant worm travelling through dunes as if they were fluid already asks us to step beyond standard biology. But once again, Dune places the impossible beside the suggestive. Real granular materials can sometimes behave in surprisingly fluid ways under vibration or disturbance. Burrowing animals on Earth exploit soil, sand, and sediment with remarkable efficiency at much smaller scales. Desert organisms are specialized masters of heat management and resource conservation. None of this makes a sandworm physically realistic in the strict sense. What it does is provide enough conceptual scaffolding for the viewer to feel that the creature belongs to the same world as the dunes, the heat, and the spice. That belonging is the true achievement. The sandworms do not feel imported from another story. They feel like the ultimate expression of Arrakis itself. Massive, ancient, territorial, and inseparable from the ecology that supports human civilization while threatening it. In Dune, the most terrifying creature is not an accident of evolution wandering the landscape. It is part of the landscape's deepest logic. That is why the planet never feels passive. Arrakis is alive through systems, not sentiment. Its desert is also harsher than almost anything Earth can offer as a direct comparison. The Sahara is often used as shorthand for planetary-scale heat and dryness. Yet even the Sahara has rainfall, groundwater, edge habitats, and large-scale atmospheric participation in a water-bearing planet. Arrakis is presented as something beyond that, a place where the familiar Earth desert becomes almost a comforting memory by comparison. This is where the world tips further from realism and into exaggeration. But again, the exaggeration is purposeful. By pushing aridity to an extreme, Dune strips away every illusion that human beings stand apart from planetary conditions. On Arrakis, the planet always wins first. And that is what makes the three main worlds of Dune so effective in relation to one another. Giedi Prime represents industrial domination, Caladan represents ecological generosity, Arrakis represents environmental sovereignty. It cannot simply be conquered by machinery, because the environment itself imposes costs too high for brute force to solve cleanly. Empire may claim it on paper, but the desert decides who actually understands it. The more closely you look, the more Dune reveals itself as a story about dependence disguised as control. The Empire depends on Arrakis. Arrakis depends on its own hidden ecological processes. The people who think they rule the planet are often the ones least adapted to it. And behind all of this, the sky remains unstable, the year unreliable, the heat relentless. It is an extraordinary example of how science fiction can use questionable astronomy to produce deeper realism about survival, power, and place. But astronomy is only the beginning of Dune's challenge. Once the world itself is in place, the story asks us to accept something even more difficult than a harsh desert planet. It asks us to accept shields that stop fast-moving weapons, ships that cross impossible distances, and a substance so valuable that human civilization bends around the minds it transforms. The moment Dune leaves the surface of Arrakis and begins explaining how its wider civilization functions, the science becomes less geological and more conceptual. This is where the world stops asking whether a desert planet could exist and starts asking whether an empire could grow around a set of impossible technologies and still feel internally coherent. Strangely, it can. Not because the mechanisms are all defensible in modern physics, but because each one is tied to a real pressure point in our understanding of nature. Dune rarely invents nonsense for no reason. It usually starts with a genuine scientific limit, then imagines what civilization would look like if that limit could be bent. Take the personal shields. They are among the most recognizable ideas in the series because they change the logic of combat so completely. In a universe with advanced machinery, firearms, and spacecraft, you might expect violence to become more distant and more automated. Instead, Dune creates a world where close combat returns to prominence because shields stop fast-moving projectiles while allowing slower objects to pass through. It is a beautiful narrative solution because it reshapes warfare through physics, or at least through a stylized version of physics. The first thing to say is that nothing in known science behaves quite like this. A field that distinguishes between fast and slow matter in so selective a way, while still remaining portable, stable, and safe to use, would require a level of control over energy and force interactions far beyond anything we understand. Speed by itself is not a simple physical category that materials or fields can just interpret as a binary permission system. Matter carries mass, momentum, charge, structure, and energy, and interactions depend on all of those properties. So if a shield can block a bullet but admit a knife moving slowly, it is not doing anything like ordinary armor. It is performing extremely fine real-time discrimination. That sounds impossible, and in modern terms it probably is. But what matters is why Herbert wanted such a technology in the first place. A shield like this transforms violence from brute acceleration into timing, precision, and nerve. It changes the human body from a vulnerable passenger of technology back into the decisive instrument. That is not really a prediction about engineering. It is a thought experiment about what kind of culture emerges when speed stops being the ultimate advantage. Even in speculative terms, though, the idea has an interesting shadow of realism. Physics does contain systems where thresholds matter. Some materials react differently depending on rate of deformation. Some protective structures dissipate energy more effectively when impacts occur above certain speeds. Plasmas, electromagnetic fields, and non-Newtonian materials can all produce behavior that feels strangely selective under particular conditions. None of this gets us to a true Holtzman shield, but it does remind us that nature is full of conditional responses. Dune takes that intuition and turns it into a total military doctrine. The same is true of the famous warning about lasguns and shields producing catastrophic interactions. This concept is even more speculative, but again it reveals a useful instinct. When very energetic systems interact in poorly understood ways, unexpected outcomes can occur. In real physics, concentrating enormous energy densities into tiny regions can produce plasma formation, material vaporization, radiation bursts, and other destructive effects. Dune dramatizes that principle to the extreme, making certain technological combinations effectively taboo. The result is a universe where invention does not remove constraints, but generates new ones. That is one of the reasons Dune feels older and wiser than many futuristic settings. It does not imagine progress as a straight line toward convenience. It imagines it as a maze of trade-offs. Every solution opens another problem. Every instrument creates a vulnerability. Every power carries conditions. This is a much more believable way to build a future, even when the individual technologies are wildly speculative. Then there is folded space, perhaps the grandest leap in the entire setting. Interstellar travel in Dune does not function as a slow expansion across the stars through multi-generational journeys or relativistic hardship. It functions through the spacing guild, whose navigators make it possible for ships to traverse enormous distances effectively instantaneously. Depending on the version of the story, this may be described less as moving faster than light and more as altering spatial relationships so the distance itself is circumvented. That distinction sounds elegant, but physics remains unforgiving. According to Einstein's relativity, faster-than-light travel is not merely a difficult engineering problem. It threatens the structure of causality itself. If information or matter can outrun light under ordinary conditions, then different observers may disagree not just about duration, but about sequence. Cause and effect become unstable. This is why so much serious speculative physics avoids saying that faster-than-light travel is easy. It is not just that the energy requirements are enormous, it is that space-time appears to be built in a way that protects causal order. One of the few loopholes often discussed is the idea of manipulating space-time itself. Wormholes, warp metrics, and other exotic geometries try to respect local light speed limits while altering the larger structure through which travel occurs. In principle, this is closer to what folded space gestures toward. The ship is not accelerating through normal space in the usual way. The route is being changed at a more fundamental level. But even here, modern physics gives us no practical foothold. Such geometries tend to require exotic negative energy densities or matter configurations that remain hypothetical at best. So Dune does what all great mythic science fiction eventually does. It keeps the language of science, but lets the mechanism drift into the symbolic. Folded space is less about engineering than dependence. Humanity has built a civilization that cannot function without navigators capable of doing what machines or ordinary minds cannot. The cosmos has been made traversable, but only by concentrating power in a transformed class of beings. That is not really a lesson about propulsion. It is a lesson about monopolies, vulnerability, and the cost of building an empire on processes no one fully controls. And this is where spice becomes the central hinge of the entire universe. Spice is not merely valuable fuel or medicine. It extends life, expands awareness, sharpens perception, and allows guild navigators to steer through folded space by glimpsing possible paths. In literal scientific terms, this is almost impossible to defend. No known substance grants stable prescient insight into future states of reality. Chemistry can alter perception, pattern recognition, memory and cognition, but not in a way that solves the problem of navigating causality across impossible distances. Yet spice still works powerfully as speculative science, because it grows from something very real. The human brain is a prediction machine. Consciousness constantly models possible futures, estimates outcomes, and interprets uncertain information through incomplete sensory input. Psychoactive compounds can profoundly alter how those processes feel and function. They can heighten salience, distort time, intensify pattern recognition, and restructure awareness. Dune pushes that principle to a cosmic extreme. It imagines a substance that does not merely influence thought, but unlocks access to a deeper layer of possible reality. Even if that is scientifically indefensible in strict terms, it remains philosophically rich. Spice makes perception itself the crucial technology of civilization. Ships do not cross space because engines have become all-powerful. They cross space because human consciousness has been modified into a navigational tool. This shifts the emphasis of futurism away from hardware and toward transformed minds. In a genre often dominated by machines, Dune insists that the most dangerous technology may be the mind when altered by ecology, scarcity, and dependence. And because spice comes only from Arrakis, the planet's environmental harshness becomes inseparable from the structure of civilization. A desert that seems barren turns out to be the source of the one substance that holds the empire together. That is scientifically elegant even when the details are not. The world that appears least livable becomes the most geopolitically indispensable. Scarcity is converted into leverage. Ecology becomes empire. Water, then, is not just a local survival issue. It becomes the moral counterweight to spice. On Arrakis, water is the measure of seriousness, because it is the measure of life itself. A society that wastes water in such a place would quickly destroy itself, so every custom, every discipline, and every technological adaptation surrounding water collection becomes a realistic outgrowth of planetary conditions. Among these, the stillsuit is perhaps the most convincing invention in the entire franchise. Unlike shields or folded space, the stillsuit does not require physics to be reinvented. It requires engineering to be pushed toward extraordinary efficiency. A garment that reclaims moisture from sweat, respiration, and bodily waste, then recycles it into drinkable form, is ambitious but conceptually grounded. Modern life support systems already reclaim water in spacecraft and closed habitats through filtration, condensation, and processing. The challenge is miniaturization, reliability, comfort, and near total efficiency under brutal heat. Dune imagines a suit that solves those problems well enough to become second skin. That is far more believable than many of the universe's flashier technologies. In fact, it may be one of the most realistic signs that Herbert cared deeply about the lived consequences of environment. On Arrakis, survival cannot depend on dramatic genius every hour of the day. It depends on systems. The stillsuit is a system. It is the body extended through engineering, much as clothing in any harsh climate becomes part of the survival apparatus. In that sense, the stillsuit belongs to the same family of ideas as Arctic gear, desert veils, diving equipment, and pressure suits. It is an adaptation layer between organism and world. The same pragmatic instinct appears in the hidden water reserves and the long dream of transforming Arrakis. Terraforming, in modern planetary science, is one of those ideas that sits on the border between technical imagination and civilizational fantasy. To alter an entire planet's climate, atmospheric composition, albedo, hydrology, and ecological cycles would require timescales, energy, and coordinated control on an almost absurd scale. Mars, for example, cannot simply be warmed by optimism. It lacks many of the ingredients needed to become Earth-like in any easy or stable sense. Arrakis would be no simpler. If its desert condition is maintained not only by heat, but by deeper ecological relationships, then changing the world would mean changing everything at once. Surface water would alter albedo and cloud formation. Vegetation would change dust, carbon cycling, and local climate. Animal life would respond. Atmospheric chemistry would shift. Hidden feedback loops could emerge in both helpful and catastrophic ways. Terraforming is not gardening. It is system surgery performed on a planet. And Dune knows that. The dream of a greener Arrakis is not portrayed as a trivial engineering upgrade. It is a civilizational and spiritual project carried through secrecy, patience, and ecological knowledge. That is far more realistic than science fiction stories that treat planetary transformation as something a few machines can accomplish quickly. In Dune, the planet has to be understood before it can be changed, and even then, the change may threaten the very conditions that made the planet valuable in the first place. That is the deeper brilliance of the setting. Every major scientific idea in Dune is tied to a contradiction. Shields preserve life but reshape violence. Folded space connects worlds but creates dependence. Spice expands possibility but enslaves civilization to a single ecology. Water is sacred because it is scarce, yet abundance might destroy the balance that gives Arrakis its power. The science does not function merely to impress us, it functions to trap the characters in systems they cannot escape cleanly. Which is why Dune remains so compelling even when its science becomes most metaphorical. It understands that a fictional technology does not need to be literally achievable to be intellectually sharp. It needs to reveal something true about constraints, trade-offs, and the price of mastery. Herbert's universe is not one where humanity conquers nature through invention. It is one where invention only deepens humanity's entanglement with nature, with scarcity, and with the hidden costs of power. And once science fiction has carried us that far, from habitable moons to sacred deserts, and from survival engineering to impossible navigation, it can turn toward a different kind of fear altogether. Not the fear of a world too harsh to tame, but the fear of travelling into the unknown and discovering that the most dangerous thing waiting there is not the planet, but the life that learned how to use it first. That kind of fear takes a very different shape in the Alien universe. Dune imagines a civilization so advanced that its deepest struggles revolve around ecology, power, and consciousness. Alien takes many of the same raw ingredients: interstellar travel, distant worlds, human ambition, unknown biology, and strips away the grandeur until only vulnerability remains. Space is no longer the stage for empire, it is distance without mercy. A signal from an unknown moon is not an invitation to wonder, it is the beginning of a mistake. That shift is what makes Alien and Prometheus so enduring. They do not merely place monsters in space, they ask a more unsettling question first. What would it actually mean to go far enough from Earth that rescue becomes abstract, time becomes elastic, and whatever you find out there may have evolved under conditions so unlike ours that the very act of contact becomes dangerous? Before the xenomorph ever appears, the franchise has already built a cosmology of isolation. Prometheus begins at one of the most ambitious points in the whole series. It suggests that ancient human cultures scattered across Earth may have left behind star maps pointing toward the same region of the sky, implying that our species was guided, or even designed, by an older extraterrestrial civilization. As a mythic premise, it is powerful. As astronomy, it immediately runs into problems. The destination implied by these maps is associated with Zeta Reticuli, a real binary star system roughly 39 light-years away in the southern constellation Reticulum. The choice is interesting because Zeta Reticuli has a long cultural afterlife in science fiction and extraterrestrial folklore. It sounds scientific because it is scientific. It is a real nearby system, close enough to feel like a plausible target for speculation, yet distant enough to preserve mystery. But Prometheus attaches to it a much stranger claim. If prehistoric humans from different parts of the world recognized and encoded this destination, then they would need a stable, meaningful way to identify stars in a southern constellation that many of them could not have seen from their own latitudes. That is the first crack in the premise. The night sky is not the same from every point on Earth. Constellations visible in the far south are not equally visible from the north, and in some cases, not visible at all. Ancient sky watchers were extraordinarily capable observers, but they were still limited by geography, precession, seasonal timing, and naked-eye astronomy. So the idea that multiple distant cultures independently recorded an exact route to Zeta Reticuli becomes very difficult to defend. It works as a story about inheritance and hidden design, but it does not sit comfortably inside real archaeoastronomy. Still, even here the franchise is doing something clever. It uses a real star system, because real coordinates always make fiction feel more dangerous. An invented destination can be filed away as fantasy. A named system with a place in the astronomical catalogue begins to pull the imagination in another direction. You start thinking not about myth, but about mission profiles. How long would it take to get there? What sort of propulsion would be required? What would communication delays look like? Even before Alien becomes biological horror, it is already engineering horror. The same applies to the moons and worlds visited in the series. The franchise loves to place its most disturbing discoveries not on comfortable planets, but on bleak satellites orbiting giant planets in remote systems. That is a smart instinct. In real planetary science, moons may indeed be some of the most compelling sites in the search for exotic environments. They can be geologically active, tidally heated, chemically rich, and hidden inside gravitational arrangements that create complexity far beyond what a simple rocky planet might offer. A moon around a giant planet is already a place where the ordinary rules of familiar landscape begin to break apart. LV-426 is perhaps the most famous example. It feels grim, windswept, industrial, and ancient all at once. The surface is shrouded in cloud and storm. The horizon is bleak. Wreckage and silence dominate the visual field. As atmosphere, it is nearly perfect. But when you start asking physical questions, the moon becomes much harder to sustain. One of the most obvious issues is size. Depending on the franchise material, LV-426 is often described as quite small, much smaller than Earth. Yet the gravity experienced by human characters seems far too close to normal Earth gravity for a body of that scale, unless the Moon is composed of unusually dense material on a level that would itself create other geophysical consequences. Gravity is not an artistic preference. It follows from mass and radius. A small moon can have substantial gravity, but only under very specific structural assumptions. And if those assumptions become too extreme, the Moon stops looking like a typical rocky satellite and starts looking like something much stranger. That matters because the alien universe usually wants its worlds to feel plausible, not flamboyantly exotic. LV-426 does not present itself as a bizarre, ultra-dense remnant object or an engineered world. It presents itself as a harsh but ordinary moon in the wrong place at the wrong time. So the gravity feels like one of those cinematic conveniences we accept without noticing until someone asks the wrong question. The actors need to move normally. The sets need to function. The illusion of realism depends on not making every footstep look lunar. In visual terms, the choice works. In physical terms, it weakens the moon's credibility. The atmosphere raises similar questions. The moon appears to support weather, wind, and an operational environment where people can move outside with significant equipment, but without being instantly crushed by impossible pressure differences or radiation extremes. That means the world must retain an atmosphere of meaningful density. Again, that is harder for a small moon than for a larger body. Low mass makes atmospheric escape easier over long timescales, especially in environments exposed to stellar wind or lacking strong magnetic shielding. Real moons can keep tenuous atmospheres under some conditions, but sustaining a thick weather-bearing atmosphere is a much higher bar. This is where the giant planet setting becomes both useful and dangerous. A large nearby planet gives the sky drama and can contribute to tidal and thermal complexity. But it can also imply radiation belts, magnetic interactions, and orbital hazards. In our own solar system, Jupiter's environment is powerful enough to make the surface conditions on some nearby moons extraordinarily difficult from a human perspective. So when Alien places human activity around giant planets, it borrows real grandeur at the cost of real danger. The setting feels right, but it should probably feel even less forgiving than it already does. Prometheus broadens that tension by moving away from the stripped-down terror of Alien and into a more openly archaeological mode. The crew is not just following a distress signal, they are chasing meaning. They cross interstellar distance because they believe a remote world may contain answers to the origin of humanity. That is one of the franchise's most scientifically interesting choices because it forces us to confront the brutal reality of deep space travel. Even at 39 light-years, Zeta Reticuli is not close in any practical sense. Light itself needs 39 years to make the crossing, so any crewed mission there, under anything like present-day propulsion, would be beyond absurd. Chemical rockets are nowhere near sufficient. Nuclear concepts help, but not enough to turn such a voyage into a manageable expedition. To reduce the trip to something like a human mission timescale, you need propulsion systems far beyond what we have built, and likely some form of suspended animation or life support architecture capable of surviving years or decades in transit. This is one place where the Alien universe becomes quietly more realistic than many franchises. It often embraces the idea of hypersleep. That may sound like a simple science fiction convenience, but conceptually it addresses a real interstellar problem. Human beings are expensive cargo. They consume oxygen, water, food, shielding volume, psychological care, and time. If a civilization could place crews into reliable, long-duration stasis, then missions that would otherwise be impossible become merely extreme. Hypersleep does not solve propulsion, but it does solve one of the most punishing biological costs of distance. That alone gives Alien's journeys a certain hard-edged plausibility. The universe does not pretend interstellar space is easy. It acknowledges, at least implicitly, that the voyage is long enough to require bodies to step aside while machines do the enduring. It is a cold solution, and fittingly so. Human presence in the franchise always feels conditional, as though the ship is the real organism and the crew are temporary passengers inside it. But even with stasis, the timescales remain severe. Travel between stars demands energy, shielding, precision navigation, redundancy, and tolerance for failure on a level that dwarfs anything in ordinary aviation or maritime exploration. A minor error in a deep space mission can become fatal years before help could ever arrive. A distress beacon from a moon is not like hearing a signal from the next valley. It is more like hearing a whisper from another century. This is one reason the Nostromo and Prometheus crews feel so exposed. They are not merely far from home. They are operating in a realm where home has almost ceased to be relevant. That vastness is essential to the franchise's horror. If the xenomorph existed in a city, it would be monstrous. In deep space, it becomes cosmological. Every corridor, every airlock, every landing site is wrapped in the knowledge that containment failure does not just mean immediate danger. It means there may be nowhere to run that has meaning. Distance amplifies fear because distance erases intervention. And that brings us back to the moons themselves. The Alien franchise understands something many science fiction stories overlook. A hostile world does not have to be spectacular to be convincing. It only has to feel as though its hostility comes from being real in its own terms. LV-426 is memorable not because it dazzles, but because it looks tired, cold, and geologically indifferent. Prometheus extends that logic into monumental ruins and engineered landscapes, but the core feeling remains the same. These are not worlds waiting for us. They are worlds that happened without us. That is perhaps the most scientifically honest emotion in the entire franchise. The cosmos is not arranged for human arrival. If life exists elsewhere, it evolved according to local pressures, local chemistries, local accidents, and local violence. It will not necessarily resemble us, welcome us, or even register us as meaningful. Alien turns that fact into dread. Exploration becomes an encounter with things that did not evolve to be understood by us. Once that framework is in place, the creature at the center of the series stops being just a monster suit and starts becoming the most terrifying kind of speculative biology, one that seems to have been shaped by a world where parasitism, adaptation, and violence were refined into a nearly perfect life cycle. The reason the xenomorph continues to feel uniquely disturbing is not simply that it kills. Countless fictional creatures kill. What makes this one linger in the imagination is that its violence is biological before it is physical. It does not just attack prey, it uses bodies. It turns reproduction, growth, and adaptation into mechanisms of horror. That is a very different kind of fear. It means the creature is frightening not only when it is present, but when it is hidden inside a process already underway. That begins with the egg. In most monster stories, the first stage of danger is obvious. You see the creature, and the threat is immediate. Alien does something more unsettling. It places the threat in a dormant structure, something organic yet unreadable, waiting to be triggered by proximity. This is one of the smartest choices in the entire life cycle, because nature already gives us many precedents for dangerous quiescence. Spores, cysts, seeds, parasites, and insect eggs can remain inactive for long periods, only becoming dangerous when conditions are right. Dormancy is one of evolution's great strategies. It allows life to survive unpredictability by pausing until opportunity arrives. The facehugger then takes the concept from strange to intimate. It is not a predator in the usual sense. It is a delivery mechanism. Its body plan, all grasping limbs, tail tension, and forced contact, is built around one purpose only: implantation. That is what makes it feel so plausible in a biological sense. On Earth, parasites often display startling levels of specialization. Some exist only to enter a host, bypass defenses, and transfer the next stage of their life cycle. They do not need elegance, they need efficiency. The facehugger is horrifying because it feels like evolution has removed everything unnecessary from the design. There are obvious echoes in real biology. Parasitoid wasps lay eggs inside living hosts. Certain fungi hijack the nervous systems of insects. Lampreys attach, feed, and persist with unnerving anatomical focus. Even the way the facehugger clamps over the mouth and forces respiration through an external organ has the cold logic of a species that evolved around host management rather than combat. It is grotesque, but not arbitrary grotesque. It resembles the kind of ruthless specialization that evolution can produce when survival depends on getting one stage of a reproductive cycle exactly right. The implantation stage is where the franchise makes its most disturbing use of the human body. The host remains alive, the body continues functioning. On the surface, recovery may even appear possible. Yet inside, another organism is using the host as shelter, incubator, and resource. This is not science fiction inventing fear from nowhere. It is exaggerating something the living world already does. Real parasites often keep hosts alive precisely because dead tissue is less useful than living tissue. Some manipulate appetite, behavior, or movement. Others evade immune response by disguising themselves chemically or by occupying tissue where detection is delayed. The chestburster takes that logic to its most violent conclusion. By the time it emerges, the host is no longer a victim in the ordinary sense, but a completed biological transaction. It is hard to overstate how much of the scene's power comes from violating our expectation that the body is a closed system. Alien tells us that the body has been opened from within, not metaphorically, but as a literal reproductive event. That lands with such force because it feels like nature stripped of every comforting boundary we usually place around it. Could such a process actually happen at anything close to the speed shown in the films? Almost certainly not. Real embryonic or larval development requires energy, material, and time. A rapidly growing internal organism would need a source of nutrients sufficient to build tissues, organs, musculature, and structural support in a very short period. A human host simply does not contain enough instantly available surplus energy to explain such explosive growth without severe prior depletion or some external biochemical miracle. In that sense, the chestburster is one of the least realistic moments in the life cycle. But the franchise understands that speed serves a narrative function. The horror depends on sudden, irreversible transformation, so it compresses the timescale beyond biological credibility, while keeping the underlying logic recognizable. A host is infected. An organism develops internally. Emergence kills the host. That core pattern is real enough to give the impossible parts traction. It feels wrong because it feels adjacent to known biology, not detached from it. Then comes the adult xenomorph, and this is where the design becomes almost paradoxically elegant. It is terrifying, but it is also deeply economical. The long, smooth skull, dark exoskeletal body, digitigrade posture, secondary jaw, and minimal visual clutter all suggest a creature built for efficiency in enclosed environments. It does not look like a decorative alien. It looks like a machine that grew. That is one reason it never dates the way many monster designs do. It carries the discipline of an evolved tool. In real evolutionary terms, the xenomorph asks for a great deal. Its size, speed, strength, and durability combine traits that usually force trade-offs. Fast animals tend not to be heavily armored. Strong animals pay metabolic costs. Large bodies require energy, oxygen delivery, and waste management on scale. Exoskeletons on Earth are excellent for smaller organisms, but as bodies grow larger, external armor becomes more difficult because weight increases and molting becomes a profound vulnerability. Vertebrates solve this differently with internal skeletons, so a human-sized or larger organism with an insect-like external shell already stretches what we know about biomechanical efficiency. And yet the xenomorph remains psychologically convincing because its body is so focused. It is not asked to do everything. It is asked to hunt, endure, infiltrate, and reproduce. The elongated head gives it an almost hydrodynamic silhouette, useful for moving through ducts, shadows, and confined spaces. The tail adds balance and weapon potential. The inner jaw is not realistic in the strict sense, but it externalizes a familiar natural principle. Many predators evolve secondary delivery systems, whether fangs, proboscises, stingers, or specialized crushing structures. Alien condenses that idea into one unforgettable anatomical gesture. Its sensory biology is equally mysterious and equally effective. The creature often seems to navigate darkness, industrial environments, and prey movement with uncanny precision. On Earth, many predators operate in sensory worlds far richer than ours. Bats use echolocation, snakes detect infrared, sharks sense electric fields. Insects track chemical trails with extraordinary sensitivity. So the xenomorph's apparent environmental awareness is not itself unrealistic. The problem is that the films wisely do not over-explain it. Once a monster is reduced to a list of organs and functions, some of its power evaporates. Alien instead lets the creature behave as though it perceives the world through channels we do not share. That restraint is one reason the biology feels stronger. Nature is often frightening, not because it is incomprehensible, but because it is intelligible only in fragments. We understand enough to know a process is real, but not enough to feel in control of it. The xenomorph occupies exactly that zone. It seems adapted, not magical, but adapted to what, exactly, remains disturbingly open. The most notorious trait, of course, is its blood. Acid blood is one of the creature's defining features because it turns injury into risk. To wound the organism is to invite collateral destruction. Floors, hulls, walls, and bodies can all be compromised at once. In dramatic terms, this is brilliant because it means conventional victory becomes dangerous. In chemical terms, it is extraordinarily difficult to justify. A fluid capable of burning through metal rapidly would need extreme corrosive properties. On Earth, strong acids and oxidizers can indeed destroy tissue and react aggressively with many materials, but they are also dangerous to the containers that hold them. Living organisms are made of vulnerable molecules. Cells, proteins, membranes, and connective tissues do not casually coexist with highly reactive fluids unless elaborate containment systems exist. Some organisms do produce acids or defensive chemicals, but these are usually stored in specialized glands, compartments, or mixed only upon release. A bloodstream functioning wholesale as a metal-eating chemical weapon is another matter entirely. For the xenomorph to survive this, its internal tissues would need to be composed of materials with extraordinary resistance, perhaps ceramics, exotic polymers, or a biochemistry unlike anything we know. That is possible in fiction, but it places the organism much farther from terrestrial life, and perhaps that is appropriate. The franchise consistently invites us to recognize Earth-like biological patterns, then reminds us that this creature did not evolve under Earth's chemistry, Earth's ecological balance, or Earth's limits of softness and fragility. The acid blood also serves another important function. It makes the xenomorph feel like a total organism. On Earth, many animals are dangerous in one obvious way: venomous, armored, fast, camouflaged. Alien gives us a creature whose threat extends through every layer of encounter. It can hide, it can implant, it can grow, it can strike. Even its wounds remain hostile. That level of integrated danger is rare, but not entirely without biological echo. Some of the most successful life forms on Earth are successful not because they are unmatched in one domain, but because many small advantages reinforce one another. That same principle becomes even more disturbing in the Queen. Social insect systems already show us how much can be accomplished when reproduction, labor, and defense are divided across castes. Ants, termites, and bees build societies that function almost as superorganisms, with the colony, rather than the individual, acting as the real biological unit. Alien borrows this concept and darkens it. The Queen is not just a larger monster, she is a reproductive center, a strategic intelligence, and a sign that the xenomorph is not merely an animal, but an ecological system in motion. This is one of the franchise's smartest expansions, because it transforms isolated horror into population horror. Once there is a queen, an egg field, and a sustainable reproductive engine, the xenomorph ceases to be an accident and becomes an outbreak architecture. It can colonize space, not just haunt it. Again, real biology gives us useful analogues. Ant queens, fungal fruiting bodies, and reproductive swarms all demonstrate that life becomes much harder to contain once it shifts from individual threat to systemic reproduction. Then Prometheus pushes the concept even further with the black goo. Here the franchise moves beyond predation and parasitism into something more like programmable mutagenesis. The substance appears capable of breaking down, rewriting, or violently redirecting living systems, producing different outcomes depending on host, context, and exposure. Scientifically, this is where the series reaches its loosest ground. Real mutagens exist. Viruses rewrite cells. Horizontal gene transfer alters genomes. Radiation damages DNA. But the black goo behaves less like any single biochemical agent and more like a narrative distillation of uncontrolled biological possibility itself. That does not make it empty. In fact, it makes it revealing. The black goo embodies a very modern fear, not simply that life can kill us, but that life can be edited, accelerated, recombined, and weaponized. It takes evolution, normally a slow and indifferent process, and gives it the speed and intent of a laboratory nightmare. What if the mechanisms that generate form were no longer slow? What if mutations stopped being blind and became invasive? What if biology itself could become a delivery system for transformation on command? This is where Alien touches one of the deepest scientific anxieties of the present age. As our ability to manipulate genes, microbes, and cellular systems grows, so does our awareness that biology is both more powerful and less morally structured than we once imagined. Life does not care whether a change is beautiful, useful, or humane. It only propagates what works under given conditions. Alien weaponizes that truth. It imagines a form of life engineering with no ethical break, no ecological restraint, and no meaningful distinction between creation and infection. And that may be why the franchise still feels so modern. Its horror is not medieval. It is biological systems thinking turned hostile. The xenomorph is terrifying because it behaves like a ruthless summary of real life's most efficient strategies. Parasitism, adaptive morphology, reproductive specialization, environmental resilience, and chemical defense are all real. Alien does not invent them, it fuses them. It turns distributed truths of Earth biology into one concentrated organism and then places that organism in environments where distance makes every mistake permanent. By the time you reach that realization, the creature has changed in your mind. It is no longer just a monster waiting in a corridor. It is a hypothesis about what evolution might produce if competition, scarcity, and replication were allowed to optimize without any requirement that the result be compatible with human survival. And once science fiction has shown us a life form that seems built from real biological principles pushed to nightmare extremes, it can widen the frame again and ask a different kind of question. Not what sort of creature could live out there, but what space-time itself might do to us if we travel far enough into its deepest distortions. Interstellar begins with something deceptively ordinary. Not a gleaming future city, not an armada, not a triumphant leap into the stars, but a failing farm. Dust moves through the house. Crops die one by one. The planet is still recognizably Earth, yet it already feels like a world slipping out of human reach. That choice matters because it grounds everything that follows in a very physical anxiety. Before Interstellar becomes a story about black holes and higher dimensions, it is a story about environmental collapse and the fear that even our home world may not remain hospitable forever. That opening also gives the film one of its strongest scientific instincts. It treats civilization as something more fragile than we like to admit. Modern life depends on stable climate, reliable agriculture, and a biosphere that remains broad enough to support billions of people. If crop blight spread across multiple staple species, and if atmospheric dust and ecological decline intensified at the same time, the problem would not just be famine, it would be civilizational narrowing. The range of futures available to us would shrink. That is why the film's desperation feels real, even before the physics begins to bend. From there, Interstellar expands outward with remarkable confidence. Hidden beneath the surface decline of Earth is a secret project built around the possibility that humanity's future may lie elsewhere. And at the centre of that possibility is one of the most famous speculative objects in modern science fiction, the wormhole near Saturn. This is where the film makes its first major leap, but unlike many films, it does not leap without touching real theory on the way up. A wormhole is not a casual fantasy object. It emerges from the mathematics of general relativity, where space-time is not a fixed stage, but a dynamic geometry shaped by mass and energy. Under some solutions to Einstein's equations, it is possible to imagine a tunnel or bridge connecting distant regions of space-time. In simple language, if ordinary travel means crossing the surface of a map, a wormhole would mean folding that map so two distant points touch. The concept is elegant because it preserves the idea that space itself can be manipulated, rather than requiring a ship to simply outrun light through normal space. That much is grounded in real mathematical possibility. The problem is stability. A wormhole that forms naturally, if such a thing can happen at all, would likely collapse too quickly for anything macroscopic to pass through. To remain open, it appears to require exotic forms of matter or energy with negative energy density, something not known to exist in the amounts or configurations needed. Tiny quantum effects can produce strange local phenomena, but scaling those effects up to a traversable wormhole is another matter entirely. So Interstellar is not showing us a likely engineering project. It is showing us a legitimate relativistic idea carried far beyond the edge of current physics. That is why the wormhole works so well in the film. It is not random magic wearing scientific vocabulary. It is a real, theoretical doorway that modern science has not been able to walk through, and the movie treats it with enough seriousness to preserve that tension. The astronauts do not behave as though wormholes are routine. They behave as though they are confronting a physical possibility so strange that even approaching it requires humility. The visual treatment helps enormously. Interstellar does not render the wormhole as a simple flat portal hanging like a hole in a wall. Instead, it treats it as a sphere, which is much closer to how such an object would likely appear to an observer in three-dimensional space. Light itself would wrap and distort around the geometry. You would not be looking at a doorway in the everyday sense. You would be looking at space-time behaving in a way your instincts were never designed to interpret. That is one of the film's quiet triumphs. It understands that exotic physics should not only sound strange, it should look strange in ways that emerge from geometry. Crossing the wormhole then opens the route to Gargantua, the black hole around which the mission's target worlds orbit. Black holes are often abused in science fiction. They become cosmic drains, ravenous vacuum cleaners, or glowing whirlpools that break every rule whenever the plot requires it. Interstellar does something more disciplined. It builds Gargantua from a combination of speculation and serious consultation, treating it not as a fantasy vortex, but as an astrophysical object whose appearance and effects follow from relativity. A black hole itself emits no light. What we see instead is the behaviour of matter and light around it. If gas and debris spiral inward, they can form an accretion disk heated to extraordinary temperatures, glowing intensely as gravitational energy becomes radiation. Meanwhile, the black hole's gravity bends the paths of photons so strongly that the disk can appear warped around the object, with light from regions behind it lensed into view. This gives Interstellar one of its most memorable images. Gargantua does not just sit in darkness, it distorts the visible universe around itself. That image was not merely artistic intuition, it was informed by relativistic modelling, which is part of why it felt so different from earlier cinematic black holes. Even the later real-world imaging of black holes and their environments has only deepened appreciation for how seriously the film tried to respect the underlying geometry. It did not get everything perfectly literal, but it aimed higher than spectacle alone. And when science fiction aims that high, even its compromises become more interesting. The greatest of those compromises involves time. Interstellar's most famous scientific idea is not the wormhole, and not even the black hole itself, but gravitational time dilation. Time in general relativity is not universal. It is affected by motion and gravity. The stronger the gravitational field you occupy, the more slowly your clock runs relative to clocks farther away. This is not science fiction at all. It is experimentally established physics. Global positioning satellites must account for relativistic effects because time does not pass identically for them and for clocks on Earth. The difference is small in daily engineering, but it is real. Near a supermassive black hole, the effect can become enormous. That is the key to the planet known as Miller's world, where a brief stay on the surface corresponds to many years passing for those farther from Gargantua's gravity. This is one of the boldest scientific premises in the film, and also one of the reasons it captivated so many viewers. For once, relativity was not just a footnote in the dialogue, it was emotional architecture. Time dilation was not a technical detail, it was grief, separation, and irreversible loss translated into physics. Could such an extreme ratio actually occur? In principle, relativity allows profound differences in elapsed time near very compact and massive objects, but achieving the exact circumstances shown in the film demands a highly specific arrangement. Gargantua would need to be enormous, rapidly spinning, and surrounded by an orbital environment delicately positioned outside the worst destructive zones, while still close enough to produce dramatic dilation. This is where the film operates near the limit of plausibility, not beyond all science, but at the edge where astrophysical fine-tuning becomes severe. That edge is still far more respectable than many viewers realise. A rapidly rotating black hole, described by what physicists call the Kerr solution, does differ significantly from a non-rotating one. Spin changes the geometry of space-time, alters the location of stable orbits, and can allow matter to orbit closer before crossing into Dune. That helps the film. A black hole with the right mass and spin can be less immediately lethal to nearby structures than a smaller black hole would be. So Interstellar is not inventing the basic principle, it is choosing the rarest and most favourable version of it. Even then, the environment should be terrifying. Radiation from an accretion disk could be severe. Tidal forces might threaten planets, oceans and spacecraft. Orbital stability becomes a serious issue. Yet the movie asks us to imagine a narrow corridor of survivability, where a planet can exist, water can remain liquid, and time can distort almost beyond comprehension. That is a large ask, but it is a large ask built on real equations rather than cinematic whim. The emotional consequences are what make it unforgettable. When Cooper returns from Miller's planet to find decades have passed for Romilly and for his children back on Earth, the film translates abstract physics into something devastatingly human. This is what great science fiction can do at its best. It does not merely explain strange science, it finds the human wound hidden inside it. Time dilation is awe-inspiring in a lecture. In Interstellar, it becomes almost unbearable. Then the film keeps going. It does not stop with one triumph of relativistic storytelling. It drives straight toward the black hole itself. Cooper falls into Gargantua, and here the movie crosses from hard science toward a more openly metaphysical register, but it still carries real physics with it. The first issue is survival. Ordinarily, falling into a black hole sounds like immediate destruction. Popular imagination often pictures the black hole as a crushing point that tears everything apart at once. In reality, the situation depends heavily on the black hole's mass. For a small black hole, tidal forces near the event horizon would indeed be catastrophic. The difference in gravity between your feet and your head would become extreme, stretching you into what is grimly called spaghettification. But for a supermassive black hole, the event horizon can be far enough from the singular centre that crossing it might not feel dramatic at the exact moment it happens. The fatal tidal forces arise deeper inside. That means the event horizon is not a physical surface in the ordinary sense. It is a boundary in space-time, the point beyond which escape is no longer possible. Interstellar uses this truth well. Cooper does not strike a wall or explode on contact with the horizon. he passes inward. Light, geometry, and causality themselves begin to change meaning. Again, the film earns some of its boldness through accuracy. The event horizon is genuinely one of the strangest ideas in modern physics, because it marks a limit not of material solidity, but of information and escape. The photon sphere around a black hole adds another layer. This is the region where light itself can orbit, at least in unstable paths. It contributes to the visual weirdness of Gargantua and reminds us that near such objects, the categories we use every day begin to fail. Straight lines are no longer straight in any intuitive sense. Seeing is no longer simple reception. Every image becomes an argument between light and geometry. And then comes the Tesseract. This is where many viewers either surrender to the film or resist it. Scientifically, there is no accepted mechanism by which a person falling into a black hole would enter a structured, higher dimensional construct from which he could interact with earlier moments in time through gravity. The movie is no longer asking whether known physics permits the scene. It is asking whether the story's larger speculation, involving future humans or higher dimensional intelligence, can turn black hole interior mystery into narrative closure. As literal science, this is the weakest part of the film. General relativity and quantum gravity do not currently offer anything like a human navigable library of time hidden inside a black hole. But it would be unfair to dismiss the sequence as simple nonsense, because it is built on a real scientific ache. Modern physics is deeply incomplete at the point where gravity, singularity, and quantum information collide. We do not know what a full theory of quantum gravity will say about the deepest interior structure of black holes, or about information, causality, and dimensional description at those limits. Interstellar takes that zone of ignorance and populates it with story. What it gains in return is something few science fiction films manage. It turns the biggest questions in modern cosmology into intimate narrative machinery. The same film that began with cornfields and dust now asks whether love, memory, gravity, and time can be woven into a single act of communication across impossible separation. That is no longer hard science, but it is science fiction in the oldest and perhaps most meaningful sense. It uses the frontier of knowledge not merely to impress us, but to test what remains human when knowledge runs out. And once Interstellar has brought us that far, to the edge of an event horizon and into a story where relativity has already wounded every relationship it touches, the planets orbiting Gargantua stop being just mission targets. They become experiments in what sort of worlds could exist under such an impossible sky. Worlds of tidal devastation, frozen deception, and perhaps, in the end, one final fragile chance at a home. A home near Gargantua would have to emerge from conditions unlike anything in the solar system, and that is what makes the final planetary sequence in Interstellar so fascinating. By the time we reach Miller's, Mann's, and Edmund's worlds, the film is no longer content to ask whether wormholes and black holes can be visualized convincingly. It asks a more difficult question. If a supermassive black hole truly dominates a planetary system, what kinds of environments might still survive in orbit around it? And what would those environments do to the people desperate enough to land there? Miller's planet is the most famous because it translates relativity into landscape. Its surface appears shallow, oceanic, and eerily exposed, while mountains of water sweep across the horizon with terrifying regularity. The visual idea is unforgettable because it makes the black hole's influence tangible. We are no longer speaking in abstract equations about curvature and time. We are watching gravity move an entire world. The film wants us to feel that every second spent there is stolen from another life elsewhere, and every wave is a visible consequence of orbiting too close to something that bends space-time almost beyond endurance. Scientifically, Miller's world is one of the most debated settings in the movie. The core idea is that extreme gravitational time dilation is possible near Gargantua because the planet orbits extraordinarily close to a rapidly spinning supermassive black hole. That part, at least in principle, belongs to real relativity. If the black hole is massive enough and rotating fast enough, There can be orbits closer in than we would expect around a non-rotating black hole, and clocks on those orbits can indeed run far more slowly relative to clocks further away. The problem is that time dilation does not arrive alone. It arrives with tidal forces, orbital stability concerns, radiation risk, and enormous questions about how a planet could form or survive in such a place. The waves are a perfect example. In the film, they are sometimes described not as ordinary storm waves, but as colossal tidal bulges caused by Gargantua's immense gravitational gradients. That is a reasonable instinct. Tides are real consequences of differential gravity. The Moon raises tides on Earth because the gravitational pull is stronger on one side of the planets than the other. Near a black hole, the differences could become extraordinary. But if those tides are strong enough to produce waves at such absurd scale on a persistent basis, then the planet is living in a regime of continuous gravitational punishment. The stability of its ocean basins, crust, orbit, and even long-term planetary integrity would all become difficult to defend. And yet there is something scientifically honest in the terror of Miller's world. It does not feel like a serene, habitable planet conveniently placed near a black hole for aesthetics. It feels barely survivable. Every feature of the environment suggests that this is not a place where life settled into comfort. It is a place where matter itself is under strain. In that sense, the movie is doing what strong science fiction often does. It takes one plausible consequence of the setting and exaggerates it until it becomes the environment's whole personality. The same tension applies to orbital formation. Planets do not casually appear wherever a story needs them. They form within disks of gas, dust, ice and debris under very specific thermal and dynamical conditions. Near an actively feeding black hole, radiation and turbulence could make conventional planet formation extremely difficult. Even if the planets formed farther out and migrated inward, the path would be perilous. So Miller's world may be one of the least likely planets in the film's system, but it is also the one most faithful to the emotional reality of what it would mean to live at relativity's edge. It turns a mathematical effect into weather, and weather into tragedy. Man's planet offers a different kind of deception. Where Miller's world is overtly hostile, man's seems at first like a frozen possibility. There is atmosphere, there are clouds, there is terrain you can stand on. It presents itself as the sort of world a desperate expedition might want to believe in. That is exactly why it works narratively, because habitability in the real universe is often not a simple yes or no question. It is layered. A planet can have some of the surface features we associate with life and still be ruinously incompatible with long-term survival. The most memorable detail is the frozen cloudscape. In the film, vast solidified formations float or tower within the atmosphere, creating a world that looks part glacier and part sky. As literal meteorology, this is highly stylized. Real cloud formation depends on pressure, temperature, condensation nuclei, and atmospheric composition, and the idea of extensive frozen cloud layers capable of supporting dramatic human encounters pushes well beyond familiar atmospheric physics. But it is not built from nothing. Atmospheres can support suspended particles, hazes, ammonia-rich condensates, methane clouds, and layered chemistry under alien conditions. The giant planets of our own solar system already show us that clouds do not have to resemble Earth's water cycle to be real. The difficulty is scale and solidity. Man's world asks us to accept a visual environment where atmospheric structures behave almost like terrain. That is much more poetic than probable. Yet again, the film benefits from choosing a direction of implausibility that still grows from real planetary science. It does not give us a castle in the sky. It gives us an atmosphere so cold and chemically strange that cloud and ground begin to blur in the human imagination. The scene feels alien because it takes categories we know and lets them overlap under unfamiliar conditions. The atmosphere itself becomes a key issue. In the film, man's world offers enough environmental substance to support landing operations and temporary exposure with advanced suits, but it does not offer true safety or viability. That is realistic in spirit. The mere presence of air tells us very little about habitability. Venus has an atmosphere thick enough to crush and cook. Titan has a dense atmosphere but lethal surface chemistry and bitter cold. Mars has an atmosphere too thin for easy human survival. A breathable sky is not the default state of a planet. It is a rare outcome of planetary history. Man's deception lies in exploiting our instinct to equate visible atmosphere with possibility. This may be why Dr. Mann himself matters so much. His fraud is not simply a moral failure. It is a scientific warning. The universe can mislead us by resemblance. A world with horizon, weather, and ground can still be almost useless. Data can be distorted. Hope can become selection bias. Human beings under enough pressure do not merely search for habitable planets. They search for reasons to call something habitable. That is one of the sharpest truths in Interstellar. Exploration is never just a technical process. It is a psychological one. Then we arrive at Edmund's planet, the least visually extravagant of the three, and perhaps for that reason the most believable. It has open terrain, liquid water, a breathable atmosphere, and a climate that appears far closer to human tolerance than the other candidates. After so much distortion, so much desperation, and so much relativistic violence, Edmund's world feels almost humble. It does not awe us by extremity. It persuades us by restraint. That alone makes it scientifically appealing. Truly habitable worlds are unlikely to advertise themselves through spectacular impossibility. They are more likely to be quietly functional. Stable temperatures, accessible water, protective atmosphere, manageable gravity, geological and climatic conditions that allow complexity to endure. If Miller's world is the nightmare edge of relativistic possibility, and Mann's world is the tragedy of false promise, Edmund's planet is the reminder that survivability may look less cinematic than danger. Even so, there are major questions. If all three planets orbit Gargantua, then Edmund's world must also exist within a system shaped by a black hole's gravitational dominance. That means orbital arrangement matters enormously. To remain relatively benign, the planet would need a distance, path, and thermal context that avoid the severe tidal and radiative hazards threatening the others. Perhaps it orbits much farther out. Perhaps Gargantua's configuration and history allow a wider corridor of survivability than we would usually imagine. Perhaps the planet formed under unusual but stable conditions after all. The movie leaves this mostly implicit, which is probably wise. Too much detail would expose how narrow the plausibility channel really is. Still, Edmund's world succeeds as the franchise's final answer because it restores something science fiction sometimes forgets. A habitable planet is not valuable because it is exotic. It is valuable because it allows continuity. It permits biology, memory, labor, grief, rebuilding, and ordinary life. In a film saturated with cosmic scale, that is a surprisingly grounded conclusion. The destination of the most ambitious mission in human history is not a wonderland. It is a place where people might simply live. And that allows the documentary's wider argument to come into focus. Across Pandora, Arrakis, LV-426 and the worlds of Interstellar, science fiction keeps returning to the same act of creative tension. It borrows from real astronomy, real physics, real biology, and real environmental logic, then stretches them until they begin to glow. Sometimes the stretch is gentle, as with habitable moons or time dilation. Sometimes it is severe, as with floating mountains, acid blood, or navigable dimensions within a black hole. But the stretch is rarely random. The best science fiction does not lie carelessly. It bends truth with purpose. Pandora bends science to ask how rich life might become under altered gravity, denser air, and a moonlit ecology shaped by another kind of sky. Dune bends science to ask what power, scarcity, and adaptation look like when a desert planet becomes the center of civilization. Alien bends biology to ask what evolution might produce if survival stripped away every human preference for decency, safety, and separateness. Interstellar bends relativity to ask how time, loss, and hope change when the universe's most extreme geometry enters ordinary human relationships. That is why these stories endure, not because they predict the future in detail, and not because every mechanism would survive contact with a careful physicist or biologist, but because they use scientific reality as a scaffold for deeper imagination. They understand that the universe is already stranger than instinct allows. Stars really die in violence. Time really does stretch. Moons really may hide oceans. Life on Earth really has evolved forms of parasitism, symbiosis, and resilience that once would have sounded invented. Science fiction succeeds when it notices that the truth is already astonishing, then asks how far that astonishment can be pushed before wonder turns into myth. And perhaps that is the real boundary we have been tracing all along. Not the line between fact and fiction, as though one side were honest and the other false, but the line where knowledge gives imagination permission to move. Cinema crosses that line constantly, sometimes clumsily, sometimes brilliantly. But when it does it well, it gives us something more valuable than accuracy alone. It gives us a way to think emotionally about realities too large, too distant, or too abstract to grasp on their own. A moon becomes a test of habitability. A desert becomes a theory of civilization. A monster becomes a study in hostile evolution. A black hole becomes a wound in time. The science is stretched, but the questions remain real. What kind of worlds can exist? What kind of life can survive? What does distance do to us? What happens when nature stops resembling the conditions that shaped the human mind? Those questions are why we keep coming back to stories like these. They reassure us that the universe can still surprise us, even after equations, telescopes, and probes have done their work. More than that, they remind us that science and imagination are not enemies. Science tells us what the cosmos allows. Imagination asks what it might feel like to stand there when allowance becomes experience. And somewhere between those two, between the discipline of evidence and the freedom of wonder, science fiction finds its most enduring purpose. It does not help us escape reality. It helps us look at reality again and notice that it was wilder than we thought.